last lecture I was talking about this well-known work of Jeremy Shukun, who tried to estimate the global mean temperature based on proxy data from ice cores, ocean cores, variety of proxies. And I said that's a challenge because these proxies don't cover the entire world. They only cover coastlines, Antarctic region, Arctic region, misses most of the land in Asia. So there is a doubt about how well can you combine all these data to get the global mean temperature. One advantage we have today is that this period from 20,000 years ago to today has also been simulated using coupled ocean atmosphere models, which were integrated from the last ice age to today by the well-known work done by NCAR, which we discussed a few lectures ago. So that, of course, being a climate model, had grid points covering the entire Earth. So one could take the climate model and take only data from these grids and find out how close these grids will give a temperature close to the global mean. That is, you can take a global mean from the climate model data, only taking these locations. Take a global average, compare with global mean calculated taking all the data that the model has and see how close they are. If they are quite close, you know that this is not a bad sample. Okay. So this issue I will take up little later in this talk. Now one thing about these proxies is they clearly show that the change from glacial to interglacial cause much more warming in the Arctic and Antarctic compared to the tropics. For example, as we came from the last ice age to the present climate, Greenland showed warming as high as 17 degrees centigrade, while tropical regions showed warming of 1 or 2 degrees. Okay. So this spatial gradient is reproduced by proxy data. This shows that proxy data are quite reliable for temperature. Now here is the important result from Shukun's paper, and what is the important result? So the blue line is the global mean temperature from the proxy data, and the red line is the Antarctic temperature from the proxy data. Okay. And you notice clearly that as we came out of the last ice age, Antarctic temperature increased first and the global temperature warmed up about 800 to 1000 years later. Okay. This is a very important conclusion of Shukun, saying that the Antarctic temperature and global temperature do not change at the same time. The Antarctic temperature changed first around 18,000 years ago. It started changing rapidly, and the global mean temperature changed much more slowly and then much more rapidly, went through a little bump during the Younger Dryas cold event and then rapidly increased to reach the interglacial conditions of the Holocene. Okay. So the key point is that as we came out of last ice age to the Holocene, the temperature of Antarctica and global mean temperature did not change at the same rate. The Antarctic changed first and the global mean temperature warmed up later. Now why is that is very clearly seen in this graph. You look at these yellow dots are the carbon dioxide, global mean carbon dioxide. Okay. You can remember carbon dioxide gas, it gets mixed uniformly across the globe. Doesn't matter where the CO2 comes out of the ocean, ultimately it is uniformly mixed. So what this shows that as Antarctica warmed up, carbon dioxide started increasing because the oceans around Antarctica also warmed up and they released carbon dioxide. And as they release carbon dioxide, the greenhouse effect of carbon dioxide was felt all over the world, and the global mean temperature began to change, okay, after the CO2 increased. And so you can see clearly right through the carbon dioxide increase is closely linked to the Antarctic temperature, not the global mean. And the global mean followed about 800 to 1000 years later. So this is a very important conclusion from the work of Shukun, which is that we know that the transition from the last ice age to the Holocene occurred in two steps. First, Antarctica warmed, and once Antarctica warmed, carbon dioxide came out of the ocean and also out of land. And as the carbon dioxide level increased from around 180 parts per million to around 200, 220, the global mean temperature started responding. Okay? And so the global mean temperature followed the increase in CO2 with a lag of around 800 years. Okay? So this is a very important piece of work based on proxy data. And so when this paper is published, the paper is only 5 pages long. All of you can read it. It's a very fine paper, but you will have a lot of questions. Whether it was the way they combined all the 80 core data was correct. So is the answer sensitive to the way they combine the data? So if you look at the questions that referees raised to this paper, those questions were answered by the authors of this publication, and so the answers to the questions read with referee is 50 pages long. It comes under the supplementary material in the journals available freely. You can look at it. So I want to look at this main paper as a supplementary to understand how scientific rigor is established today, okay? Because some of this is not known to many of you, because you have not seen a response of the authors to the various doubts that were raised by the referees. Okay? Normally referee comments are not easily available, although today the many journals give access to referee comments. So I am going to now look at some of the referee comments and how the authors are able to handle it. Okay? There is one more look at the Shukun's paper's graph, slightly easy to understand. See the rapid temperature rise around 18,000 years ago in Antarctica, which triggered an increase in carbon dioxide, and once carbon dioxide went up to such a high value, you can see that the global mean temperature followed. Okay. So I am going to look at the 50 pages of supplementary material of this paper, in which the authors justified the accuracy of the method that they used. So the key point is the initial increase in CO2 occurred around 17,500 years ago. At that time, the global mean temperature had not changed. Okay. So once the CO2 increased, deglacial warming started, and this early warming occurs in two phases. First, a gradual increase, okay, and then a rapid increase. So you can see that there is a gradual increase, there is a rapid increase. Okay. So this difference is what they are pointing out, that the initial effect of albedo change due to melting of the glaciers was not much, until carbon dioxide increase added to the albedo change to increase the rate of global warming. So, the key point is ice melting alone would not have caused us to go from the glacial phase to the Holocene, because that rate of change is too slow. Okay, you see here. Okay. So, that rate had to be amplified by the carbon dioxide feedback, and once carbon dioxide increased, and so did methane, which we will see later. So, combination of these two increase the greenhouse effect dramatically, so double the rate of increase of global mean temperature. So, this is a clear show that yes, initially ice had to melt due to the solar radiation increase around 18,000 years ago. The peak of the radiation was at that time. It melted the ice, but ice melting alone cannot end the ice age. It required the trigger of a CO2 increase, which was triggered by the increase in Antarctic temperature. Notice Antarctic temperature increases faster than the global temperature. Okay. So, Antarctic behaves somewhat differently from the rest of the world, okay. And so it started increasing in temperature first, that increased CO2, then CO2, which was globally well mixed, added to the decreasing albedo of the earth due to ice melting. It added the second feedback of carbon dioxide, and later on of course water vapor. All these combined to increase the global mean temperature much more rapidly than before. Of course, there was a slight delay due to Younger Dryas event here, but there was only a few thousand year blip, and then it went back to the same rate as before. So, I want you to understand the difference between the initial warming, which was triggered only by ice, and the later warming, which was both due to ice and CO2. So, both ice albedo feedback and the CO2 methane greenhouse effect feedback worked together to increase the global mean temperature at a much more rapid rate than before. But the key point is that the work of Shukun shows that the initial CO2 increase occurred due to Antarctic warming, not global warming. That is the main point. Okay. Now, what happened in the Antarctic? Now, let us see a close up of the increase in CO2 here in blue and Antarctic temperature in red. Okay. There is a lot of noise here because system is not a very stable system, so fluctuates a lot of the order a couple of degrees in Antarctic temperature. So, you can see the Antarctic temperature started increasing around 70,005 years ago. You can see this change in slope here. Okay. Clear change in slope. Okay. And once the slope increased, within a few hundred years, around 800 years, CO2 started rising. Okay. So, Antarctic temperature rise occurred first, and this was followed 800 years later by the CO2 increase. Okay. And when Antarctic temperature rise was somewhat halted during the Younger Dryas cold event, so did CO2, but after 800 years. Again, when Antarctic started increasing again, then CO2 increased again. So, I want you to see the clear connection between the increase in Antarctic temperature first, followed about 800 years later by the increase in carbon dioxide, and that carbon dioxide increase occurred globally, not locally. Okay. It was triggered locally, but the response was global. Once more we look at the fact that CO2 increase and temperature increase in Antarctica went together, but the global mean temperature occurred 800,000 years later. Okay. Now, so this is one more example of this graph. Here it is a little more complicated. If some of you can appreciate that, that will be nice. It shows temperature at various latitudes. Okay. This is the southern hemisphere, 60 to 90 south. This is the northern hemisphere, 60 to 90, northern polar, southern polar. I want you to notice that the fundamental difference between southern polar region and northern polar region. Southern polar region shows somewhat smooth variation in temperature from the last ice age to the Holocene, but the northern hemisphere in this purple line shows all kinds of ups and downs. Okay? And this down is due to Younger Dryas cold event. This is the Berlin-Elleroy warm event. So, these fluctuations do not occur in Antarctica. Antarctica behaves differently than Arctic, because in the Arctic region there is a lot of land. You look at 60 to 90 north, there is a lot of land in North America and Eurasia. Okay? When you go to southern hemisphere, although Antarctica is a continent, you go 60 south and 90 south, most of it is ocean. Okay? Ocean has a large thermal inertia, so it does not show the kind of fluctuations that you see over the northern hemisphere polar region. Okay? So, this shows the clear difference between the temperature variation in the southern hemisphere and northern hemisphere. Okay? And I want also for you to appreciate that the variation in the southern hemisphere and northern hemisphere can go in the opposite direction. This is the bipolar seesaw we talked about when we were discussing AMOC. Okay? So, when there was cooling during the Younger Dryas event in northern hemisphere, there was warming in the southern hemisphere. So, this can only be explained with the role of AMOC. So, if there is a lot of ice melting and breaking from the glacier onto the water, it will slow down the AMOC. If it slows down the AMOC, the Antarctic temperature will have to rise. So, heat is not being taken out of Antarctica and brought into Arctic. So, it will warm up Antarctica. That is what we are seeing here. The impact of changes in Atlantic meridional ocean circulation. So, let me again summarize Shakun's paper. Increase in summer insolation in northern hemisphere around 20,000 years ago, and increase in mid to high latitude northern hemisphere, melting of ice, collapse of the AMOC, which leads to cooling of the northern hemisphere and warming in the southern hemisphere. The delayed warming in Antarctica is due to thermal inertia of the Southern Ocean. Southern Ocean contains a very thick mixed layer which will not immediately react to changes in incoming radiation. The rise in atmospheric CO2 occurs as a result of temperature change, and it takes along tropics also while warming, but the carbon dioxide increase that occurred is a globalizer of the deglaciation process, so that it contributes to changes everywhere, not just in southern hemisphere. Okay? So, the link between northern and southern hemisphere are twofold: one through the atmospheric carbon dioxide in the ocean, and through the Atlantic meridional circulation through the ocean region. So, ocean changes are triggered by AMOC, land changes are triggered by carbon dioxide. Now, what people have done is, because we have access to climate model simulation, we have access to proxy data, but proxy data is not equally spaced in time, and there are errors in proxy data. So, in today's world, when you have output from a climate model and output proxy data, the best way to combine the strengths of these two data is to do what is called analysis. That is, you combine these two. Wherever the proxy data is reliable, you rely on proxy data. Wherever climate data is available, you take climate data. So if you do that, if you combine all the observation with climate model simulation, you get what is called the last glacial maximum reanalysis. That is, they looked at all the data of last 24,000 years from the proxy data, related it to what's available from the climate model that I just discussed, and they came with a proxy, which is a proxy of the tropical temperature. Okay, so that was done. So reanalysis combines proxy data and climate model data to produce a more reliable data that overcome the limitation of both proxy data and climate models. Remember that climate model has its own difficulties because it doesn't resolve all the scales that you want to resolve. Now let me combine this with sea surface temperature data. Last time we discussed only the ocean cores and the ice core data. Now we look at sea surface proxies, which are plenty because you can go to the ocean and drill any number of ocean cores. Okay, and you can see here in each latitude bin here you have 50 to 100 points, which is the advantage of ocean core for sea surface temperature determination. Now this formula for getting temperature from the calcium carbonate from the shells, as well as the temperature of seawater from the O18 from seawater, can be combined to give you global mean temperature. Okay, this is the sea surface temperature. Now this is what you get from reanalysis. Reanalysis is a fusion of the observation and model output. So wherever the model is got a lot of data, you use model, not the observation. Wherever you don't have enough model results, you can go to observation. So this temperature times is a non-southern hemisphere reproduces clearly what happened during the last million years, and it also shows the interglacial answer. Now the advantage you see of this is that you have lots of model data available for validating the proxy data from ocean cores. So you can see that samples are present everywhere, and so we have a lot more faith in the reanalysis data than in just observation alone. Now again I want to remind you that Antarctic temperature warmed up gradually, but of course with a few ups and downs due to various glacial phenomena. But what I want to notice is that the Antarctic temperature does not resemble the Arctic temperature. Now this must be understood that Arctic and Antarctic vary in different time scales. Now the reason why I want to highlight this is because at some times the Arctic and the Antarctic go in the opposite direction. Look here, when the Greenland was warming up, the Antarctic went through a decline in temperature. So a lot of people could not understand why, when the Antarctic is warming, when the Arctic is warming, why is the Antarctic not warming at the same rate? So this requires further examination. So here we have proxy global mean reconstruction, based on different proxies. Okay, blue is one proxy, red is another proxy, yellow is the magnesium calcium ratio which reproduces temperature very well, and all of them together. Okay. So, I want you to appreciate the fact that although they differ from each other, they are not identical, still they broadly reproduce the fact that the global mean temperature remained fairly constant, and then around 70,500 they started rising rapidly and reached a peak around 10,000 years ago and started cooling slightly. Okay. Now, we have only 50 ensemble members from models to assimilate with the global mean temperature. So what it shows is that yes, the different proxies give slightly different temperatures, but the time at which the global temperature suddenly starts rising is almost same in all the three cases. Okay? So that's the point I want to make. Three different proxies give me the same result, so I trust this proxy. Now, the other way to understand this is doing what is called empirical orthogonal function analysis. This is to look at the global picture, not the local, and so they are able to show two major kinds of variation. One, warming occurring in the European and North American continents, okay, which is also there in the Antarctic region. But there is also another mode which is opposite in the two hemispheres. This is a bipolar mode in which southern hemisphere is warming, but northern hemisphere is cooling. And if you remember the last few lectures, this cooling is due to the ice breaking up and falling into the Atlantic Ocean, and it stops the Atlantic meridional ocean circulation, and because of that Antarctic warms up. This warming of the Antarctic is connected to the cooling of the Arctic, okay? And the link is the ocean. So you must understand, and the complexity of the problem here, the northern and southern hemisphere are linked together by the AMOC, okay? But the Earth's atmosphere is connected everywhere. The carbon dioxide that is released from the ocean due to Antarctic warming is causing CO2 to increase everywhere, along with methane and of course water vapor. All these add to the greenhouse effect and causes this warming, which is the warming which is the dominant mode here, okay? This one, okay? So this is the bipolar mode, this is the global temperature increase mode, and so both these combined gives you the final picture, okay? So you can see that the AMOC variation, which is related to EF2, is related to the PC2, the time variation of this EF2. EF1 time variation is here. So this graph clearly explains why the temperature change from the last ice age to the interglaciers did not occur smoothly. It is because changes in AMOC cause both warming and cooling in the two hemispheres, and so you have to combine this and this to get the global mean temperature of Shakun. Okay? Shakun's work is global mean, he combined all the regions. Here we are looking at the two modes of variation, one where the entire globe varies in one direction, one in which it is bipolar. Okay? So I will stop here and continue this in the next lecture, because this is a very important paper and a couple other papers which come together. So this caption for figure 3 is giving the detail, and that we will discuss in the next lecture. Thank you.